So, welcome back. Now, we start looking at this topic called rule based expert systems. This topic is more in the area of knowledge representation and reasoning, but our interest is in how that is implemented, because there is an interesting algorithm that is sitting behind such systems. So, we begin with this idea that we are looking at patterns in the domain essentially. So, earlier what we have done is that we have looked at transition and search in state space, we started with that. Then we also said that we can do transition and search in the solution space. After that we moved into problem decomposition, we saw that goals can be broken down into sub goals, and this gave us this idea of goal trees and the algorithm AO star. Now, we look at the notion of patterns inside the state. So, what is really happening behind the scenes, so to speak? What is inside the move gen function? How do you implement a move gen function? And we will see that it is basically a collection of pattern action responses. So, we are interested in this pattern action pairs, and we will make that explicit now essentially. So, in some sense we will dismantle the move gen into individual moves like we did in planning algorithms essentially. So, we say that pickup is one move, put down is another move, and so on. In a similar fashion, we will look into a general problem of reasoning and search. So, this area is also has been known as pattern directed inference systems, in the sense that you look at a pattern which is a part of a state and do something with that, and then you modify that part of the state essentially. So, a rule, and we will look at this notion of a rule here, looks at a part of the state which matches a pattern as shown on the left and modifies it to result in a new state. This idea is very similar to the idea of a rule that we use in logic, because in logic also we have a set of antecedents and then we have some conclusion essentially. But when we look at this language that we are looking at today, we will see that the right hand side will be not just conclusions which are based on the antecedents, but may have other actions included also. Amongst them would be the action of deleting a statement essentially, which is not the case in first order logic. In logic, once you say that something is true, then it kind of remains true forever. So, the Pythagoras theorem, for example, is always true. So, there is no notion of time in mathematical logic, statements are true or false essentially. And we saw that to get around this problem, when we looked at planning, we had to explicitly add predicates or delete predicates. A similar idea is followed in rule based systems as well. So, earlier this was our notion of a move gen, that you were in some start state or some any state n, and a move gen function told you what are the neighboring states. But what is inside, what is underneath the hood of the move gen function? So, a state is essentially a set of sentences in some language. By now, we have this notion of logic and language, and we saw that in planning also. Pattern is a subset of sentences, and modifying the state in a piecewise fashion. So, you look at a pattern and modify that. So, a move is basically spot a pattern and do or suggest the corresponding action. So, a state may have many patterns, and each pattern may trigger some action which will show up as in the move gen function as one move. So, these 4 moves that we see on the screen are essentially 4 patterns that can be spotted in the state and resulting in changes in that, which gives us the 4 neighbors. This idea of rule based system extends beyond simply doing search for problem solving, and it extends beyond reasoning itself. We have already seen earlier, or we have mentioned that Kowalski had said that logic can be used for programming, that logic subsumes computation essentially. So, that is how we got the idea of logic programming. Declarative programming is a general term which talks about programming where you specify the relations between things and do not specify the sequence of actions that have to be done in the program, which is typically done in imperative programming languages. For example, C, that you do action A, you do action B, and so on and so forth. In declarative programming, we do not worry about which action is to be done, we worry about the relation between the input and the output essentially. And we see that a rule associates an action with a pattern in the state. The community also call it a production. So, sometimes people call it a rule based production system. Unifying format for heuristic knowledge, business rules and actions. So, a rule can represent an action also, like in the planning operators pickup or something. It can also encapsulate heuristic knowledge, and this is the key that we want to look at here, is that human experts may give us a whole plethora of rules which they feel are useful, and in some sense in those rules we are capturing their knowledge, which we will use as heuristic knowledge. And we will see that business rules is going to be one of the subsets of this heuristic knowledge. For example, bank may have its lending rules essentially as to when do you lend to somebody and so on. Everything can be implemented as rules. So, the rules in a production system, they are a unifying format. Not only do they capture the sequence of moves you want to do, but they also capture heuristic knowledge and other related things. So, because of which declarative programming is also a Turing complete programming language, and by Turing complete we mean that anything that can be computed by a Turing machine. The Turing machine is the most general form of an abstract machine essentially. So, you might have studied that in the course on formal languages, but even if you haven't, but basically a Turing machine is an abstract computer which captures what can be computed essentially, and any programming language which allows you to do that computation would be a Turing programming language, and the language that we will look at today called OPS5 is one such language. The key thing about declarative programming is that the user or the programmer only states the rules. We already said that the rule is a connection between a pattern and an action. It is very popular in business environment. For example, I just said that lending by banks, a bank manager only needs to specify what are the rules under which somebody is eligible for a loan. The programmer only specifies the pattern action association. She does not specify when that action should be executed, which is what happens in imperative programming, that you say, okay, do this action, then do this action, and those actions may be conditional statements. If something is true, do this, or if something is not true, do that, which can be extended to things like loops. So, for example, they are also conditional actions. While something is true, do the following set of actions and so on. In declarative programming, we do not do all that. We just say what is the relation between patterns and actions, and we leave the decision of what rules to execute to as we will see, what is called an inference engine, and which incorporates a search strategy as to which rules are applicable, which ones to apply. So, the user is typically given a choice of strategies by a production system implementation, and we will see that today. So, this is a notion that we are looking at, rule based production systems. It has the following three components. One is the working memory. So, if you think of that rule based production system as an agent which is trying to solve a problem, then the working memory represents the current state of the problem solving. So, in some sense, if you remember what was happening in the planning domain, is at any given time we knew which predicates were true. Block A was on top of block B, and block C was being held by the robot arm and so on. Everything that is represented is the current state, and that we will call as the working memory. So, it contains a set of records of statements known as the working memory elements. So, working memory elements are elements which reside in the working memory. So, each of them will be called a WME. And we tend to think of this working memory as a short term memory of the problem solver, because it is dealing with the current situation, what is true at a given state or a given point of time. Then we have a set of rules essentially, and each rule, which we also call a production, it represents a move. It has typically a name or an identifier, has one or more patterns on the left hand side, which we will call as LHS or left hand side, and has one or more actions on the right hand side, which we will call as RHS side. So, the rules is the problem solving knowledge of the agent. It is independent of the current problem that you are trying to solve. It is independent of the situation, the state of the current problem, which is captured in the working memory. So, in that sense, it is a long term memory of the problem solver. The long term memory is the problem solving knowledge that the agent has. And then finally, as I said, we have something called the inference engine, and it is the task of the inference engine to first match patterns in all rules. So, each rule has a set of patterns, we have said one or more pattern on the left hand side. So, it is the job of the inference engine to look at all the rules and all the patterns in all those rules and match them with the working memory, which tells us whether the rule is applicable or not in a given state. After matching all the elements, it has to pick one matching rule. So, we assume a sequential form of execution in which one rule is fired at a time essentially, and it has to execute or fire. These are the terms we use interchangeably, that we fire a rule or we execute a rule, and we will see what all the details of all this different kind of actions we can do, and essentially it repeats this process till some termination criteria. So, what is this that is being repeated? It is a cycle of match where you match all the rules with all the working memory elements, then you resolve as to which of those matching rules you want to select essentially, and the third is fire, that having selected the rule, fire that rule, which means that you may be making some changes in the working memory as a consequence of that, and this happens till some termination criteria is used. So, as shown on the right hand side, an inference engine basically works in this cycle: match, resolve, execute, till somehow it gets out of that essentially. So, the first phase of this cycle is match. The match takes as input all the rules, that is a long term problem solving memory of the agent, and the working memory, which is the short term memory, which says what is the problem we are solving and what is the state of solving that problem, and it produces a set which traditionally has been called as a conflict set. So, the match algorithm takes a set of rules and the set of working memory elements input and generates the conflict set. Each element in the conflict set is a rule along with the identities of the matching working memory elements. We will see how they are identified in a moment, but basically every element in the conflict set is a rule and the data that it is matching in the working memory essentially. Now, we have to select between the rules in the conflict set and the matching data, and in that sense there is a conflict as to which rule to fire, and conflict resolution, which is the next stage or resolve, decides as to which of the rules to select from the set of matching rules. What are the set of matching rules? These are the ones which have been identified in the conflict set. So, the first state, the match state, results in the conflict set. Now, if you think of this problem a little bit, you will see that supposing you have 100 rules, and let us say each rule has 5 conditions on the left hand side, just for the sake of argument. So, there are 500 patterns in those 100 rules, and if the working memory has, let us say 10,000 elements, then all these 500 patterns have to be matched with all the 10,000 elements to see whether there is a match. So, it has been stated that match is the most time consuming part of a rule based system. So, having got the conflict set, the next stage is resolve, and what does resolve do? It selects one rule along with the matching working memory elements. So, it selects rule to be executed or fired plus the data which is matching that rule essentially, because that is what is stored in the conflict set essentially. And we will see that it is resolve which captures the strategy that will be used for search. The rules for conflict resolution will give you what is the strategy of search that this agent is doing. So, it is also doing search, it is all these rules are matching. Just think of it as forward chaining. In fact, the inference engine that we are looking at is also called a forward chaining rule based system, because you have the data, you match all the rules, and you in some sense you are doing the move gen function, and then you select one of them, and that selection is the crux of whether you are solving the problem efficiently or not essentially. And that selection is done by a module which does resolution, which is called a conflict resolution module. And the last stage of the inference engine is that you execute the rule plus data that you have fired, and actions that are executed, they may make changes in the working memory, which is of course then updated, and then you have a new working memory element. And if you are adopting the brute force approach, then now again you will take all these working memory elements, let us say there are 10,005 or something like that, you have added 5 new elements, which those 500 patterns in those 100 rules you have to do all over again. So, of course, one of the things we will see is an implementation, an efficient implementation in which this brute force work is not to be done, but we will come to that later. So, there is a language which started this all, a production system language called OPS 5. It was devised by Charles Forgy in Carnegie Mellon University in the 1970s. Remember from our history of AI that CMU was a very prominent center for AI, with Simon and Newell working there and many of their group. OPS, some people say in quotes, stands for official production system language, so OPS 5, but there were later versions of OPS language, and much later there is a system called SOAR. You should look it up on the net, which is was implemented by somebody called John Laird, also at CMU, and it is a cognitive architecture. Whatever I am writing. And by our cognitive architecture, we mean a set of modules or program which does what some people call as cognitive computing, which basically tries to do computing like we do essentially. And remember that that was the goal of Simon and Newell. Their first book was called Human Problem Solving, and they tried to see how humans solve problems. So, this SOAR was basically eventually evolved out of OPS 5. It contains all the elements of OPS 5, but it also contains other elements. So, nowadays if you go and download SOAR, you will see that it has a reinforcement learning component and various other components essentially. So, it kind of system which is tuned to solve problems. But coming back to OPS 5, in OPS 5 a rule has this simple form that you start with the initial P. P basically stands for production. Then you give a name to the rule, which is the rule name. Then you specify the left hand side, and then you specify the right hand side separated by an right arrow essentially. We often use the term expert system, at least in the 80s we used to use the term expert systems, because these were programs which had knowledge acquired from domain experts. And the whole idea was the domain expert would express their knowledge in the form of rules, and then we will put those rules into production system like OPS 5, and lo we would have the knowledge to solve problems essentially. One of the earliest systems was called R1, and we will look at an example of a rule from R1 in a moment. So, let us talk about the syntax of this language. So, this OPS5 is a language which is a Turing complete language, and anything that you can do in OPS5. The data structure used in OPS5 is a structured record which starts with a class name and a set of attribute names. Attribute names are marked by the hat sign essentially. The data is a collection of attribute value pairs bunched together. So, there may be a set of attributes and we will see examples, and each attribute will have a value, and so we have this attribute value pairs and they are all bunched together. The way that we implement these inference engines, the order of attributes does not matter. So, you can state them in any order and the system will work well, which is different from, for example, matching in logic where the order matters essentially, and we saw this example of backward chaining earlier. The default value of an attribute is nil. If you do not specify a value while creating a working memory element, then its value will be given as nil essentially. So, here is an example of a working memory element. The class name is student, then there are attributes. Name is an attribute whose value is Sudhir, age is an attribute whose value is 19, semester 3, discipline math, degree BSc for example. This is an example of a working memory element. So, you have a set of attribute names and you have a set of values for those attributes essentially, and then there is of course the class name. In this case the class name is a student, or the record name if you want to use that term. So, the working memory is basically a collection of working memory elements as we have said, and Simon and Newell model the working memory as a short term memory of the problem solver. That is what we have already said, that it contains the data that the solver is currently working with essentially. It is a collection of working memory elements that we have stated, and these are indexed by a time stamp. So, every working memory element is given a time stamp indicating the order in which they were added to the working memory. We will see that this will have a role to play in conflict resolution, that you may want to use that time stamp for resolving the conflict in the conflict set. So, here is an example of what a working memory could look like. So, there are 6 records or 6 working memory elements. Each of them has a time stamp given to this. Each of them has a class name. So, next or total marks or array or so on. Each of them has a set of attributes and each attribute has a value essentially. So, the first working memory element here says that the class name is next and the attribute is called rank and the value is 1 essentially. We will see how to use this because we will see examples of rules which use these particular working memory elements essentially. The second one says the class name is total marks, then there is a student who has marks and whose rank is nil essentially. So, you can imagine that we are writing a program that we have marks of all the students and we want to assign them a rank essentially, and what this working memory at this point says that the next rank that you want to assign is 1 essentially. And then of course, we will choose a student with the highest rank. In this example, it would be Sangeeta. We will assign the rank 1 to Sangeeta and then this next rank will get modified to say 2 essentially. So, the next person to get a rank will get 2. So, we will see how this is done with rules essentially. The other example that we will also see is if you have an array of elements where using the syntax of OPS5, this array can be stored by a set of records where there are 2 attributes. One is the index of the array and the other is the value stored in that index essentially. So, here we have index 1 value 29, index 2 value 12 essentially. There should be a closing bracket here. Now, let us come to rules essentially. The left hand side of a rule is a set of patterns that conform to the syntax of the working memory elements, because after all we have to do matching essentially. The value field in patterns can have variables and they can also have Boolean test. So, we are talking about the values of attributes. In a rule, you can have variables, and you can also say that do some test on whatever is stored in that particular attribute in the working memory element essentially. There may be even negative patterns to which will say that this pattern, this working memory element with this pattern should not exist in for this rule to be matching. Remember that the left hand side of a rule tells you when is a rule applicable or when does a rule match essentially. So, here is an example of a rule in English. If the next rank to be assigned is R, so notice that we will use these angled brackets to represent variables essentially, and that is a convention used in Ops 5. And there is a student who has some marks which we have written as M, which is a variable, we do not know how much is the mark, but who has not been assigned a rank as yet, and there is no student. So, this is the negative pattern that we were talking about, that there should not be any student who has higher marks than M and whose rank is also unassigned. So, basically the person with the highest marks who has not been assigned the rank is captured by this left hand side, and in Ops 5 it would look like this. Let us say we call this rule as ranking, that is the name of the rule. Remember that the syntax of a rule says P followed by rule name followed by a set of patterns. There are 3 patterns in this, and we have said that next rank to be assigned is something which is a variable called R, and total marks, there is a record of total marks for some student S, we do not know the name, who has got some marks M, again we do not know what is the marks, but who has not been assigned the rank. So, the rank is nil, and there is no record of the kind total marks where the marks are more than this variable M and the rank is also nil essentially. So, you would also see that patterns do not have to conform to the whole structure of the working memory element, you can only selectively choose attributes that you want to talk about, and then there would be some right hand side. So, again to repeat, this rule says the first condition is that okay, what is the next rank to be assigned, this tells us that. Then it says who is a candidate for this rank, that candidate must be some student who has got marks M, and there is no student who has got marks more than M. So, remember this Boolean test we had said, this will return true or false essentially. So, there must be no one with marks more than M. So, here is an example of a rule from this system which I mentioned R1, which is also called XCon. It was written by John McDermott, and John McDermott, if you remember, was an author of one of the early good books on AI, which was written by him and Eugene Charniak. So, Charniak and McDermott is how we typically refer that book to. This system called R1, internally it was called XCon for an expert configurer program, was a production rule based system written in this language Ops 5 in 1978, and it was used to assist in ordering of DEC wax machines, computer systems, by automatically selecting the systems. Now, 1978 was a time which many of you may not have been around, when there was no personal computers. I mean, not to speak of mobile phones or smartphones, there was nothing of that kind. The only computers we had were called as mainframe computers, and they were kind of machines which occupied a large amount of space in a room. And the company DEC also produced this series of very popular machine called wax computers, and this program was used to try to configure as to what is the configuration that a particular user wants to buy essentially. So, this is just an example of a rule from R1, we do not want to go into the details. The rule has a name, as you can see it is a long name, assign UB modules except those connecting to panels 4. So, this is a series of 4 such rules, this is the 4th one in the series, and there are various patterns. The current context is assigning devices to universe modules, and there is an unassigned dual port disk drive, and so on and so forth, and then you of course do this assignation. So, this is just to illustrate a kind of rule that Ops 5 uses. Of course, this rule is not in Ops 5 language, this rule is a expressed in English, just as we express the ranking rule in English first, but it can be converted into ops5. So, let us go back to the syntax where the conditions in the left hand side. What can be the conditions? The value field in patterns, remember that a rule is a set of elements which we call as each is a pattern in the left hand side. They can have, as we have said, variables and Boolean tests essentially. So, a variable Boolean test for example can be equality, which says that they are the same type as and also equal. So, for example, x equal to 3 if you say, that means that it will match only when x equal to 3 essentially. Or we can also just only take for same type, that both are integers for example. For integers or for floating point, we have this ordering relations less than equal to, greater than equal to. We also have conjunctions that two tests must be satisfied, that it must be greater than 3 and it must be less than 3.5, and there is an implicit and this is represented by this curly brackets for saying that I am talking about a conjunction. If you use two angle brackets as the one shown in the bottom, then it is a disjunction or an or essentially. So, supposing we are talking about the day of the week, then then the rule will match either if it is Monday or if it is Wednesday or if it is Friday. So, what about the right hand side? The right hand side of a rule is a set of actions that we have said. The simplest action is to make or create a new working memory element, which is called make in ops5, and other is to delete one, which is called remove. So, this is a little bit like the add list and the delete list we saw in the strips programming language or PDDL 1.0. Modify is just a short form for removing something and adding a different one, which is slightly modified. But there are other actions like read from the screen or from a file, write to a file or from a screen, load a file or halt, all kinds of things which are necessary for making it a complete programming language. So, here is our ranking rule that we started looking at it. This was the left hand side, that there is the next rank to be assigned is R, and there is some student who has got M marks and there is no student who has got more than M marks. Then what we want to do is to assign for this student the rank which is given to us in the first pattern. So, this is expressed by saying that modify the first working memory element modify the working memory element which matches the first pattern in the rule to R plus 1, which basically the next rank will become whatever R was plus 1, and modify the second element to the value R. Now, I purposefully written this in this order because if you are an imperative programmer, then you would say that the value of R has changed before you have assigned the rank. That is not the case in ops5. Actions can be thought to happen concurrently essentially, which means you are not saying that the first action happens first and then the second happens. The values that the variables you use are the values they got from match essentially. So, basically this R and this R is the same, even though this R says that you modify this to R plus 1, but it does not affect the fact that the current student will get this rank R essentially. So, if you have found the record with the highest marks, then assign rank R to the student and increment R also. There is no sequence, that the kind of confusion that would happen in imperative programming, that if you say R is equal to R plus 1 and assign rank R to the student, that means the incremented rank would be assigned, but this is not the case. The R that is used is the R that the inference engine has got in the match phase essentially. We can also use an alternative syntax. Instead of identifying the working memory from the matching pattern, that pattern number 1 or pattern number 2, we can actually give names to patterns. So, we say this is a rank and this is a total, and then we can say modify rank and modify total. It is just an alternative syntax which you may find it useful, especially if you are going to be playing around with your rules and modifying them, and then you do not have to keep track whether it is the first pattern or the second pattern, you can remember them by the names essentially. So, just a very quick example of how rule based languages can be quite powerful. So, let us look at a problem of sorting. We have already seen that there was some working memory elements in a class called array, which had attributes index and values essentially stored with every index value. The objective, so let us say sort the values in increasing order essentially. So, we have a set of records which is array index 1 value something, array index 2 value something, in array index 3 value something, and you want to sort them in increasing order. And there is a simple rule which, as you can see, is very similar to what we did earlier. What are we saying here? We are saying that for some index I, if the value is x, and if for another index j which is greater than I, so j is greater than I, the value is y which is less than the value in x. What does it mean? That there is a higher index, higher meaning numerically larger index, but whose value is smaller. So, we basically do not want it essentially, and modify, we simply say modify the first value to y and modify the second value to c. So, what have we done? We have swapped this record which was at ith index. So, for example, array 9, actually I should write let us say I will just use index I here 9 and value 6. Let us say this is one record, and there is another record whose index is more than 9. So, let us say it is 11 and whose value is less than 6, which means it is 3, let us say, for example. So, if we have these two elements in the working memory, so the 9th record has a value 6, the 11th record has a value 3, but we want to arrange them in increasing order. So, essentially we are going to swap these two elements essentially, and that is what is happening here, that whatever was stored in the second element, now that is got into the first element, and whatever was stored in the second thing has gone into the second element. So, basically we have swapped, and this one rule is enough to sort this whole array essentially. It will just repeatedly fire till there is no mismatch somewhere. Of course, this is not going to be an efficient algorithm to sort this thing. We know that sorting has to be done much more carefully, but this simply shows that a rule can capture this whole process essentially. If you are working with ops5, you can actually write algorithms like merge sort or quick sort and so on, which are more efficient, but this was just to illustrate this idea. So, we will take a break and we will come back to looking at how conflict resolution happens. Yeah.
My doubt is the 1 and 2 referring to the index, the modify 1, modify
Yeah, not the index.
Okay.
It refers to, this is the first pattern and this is the second pattern. So, that is what we saw here. Here also you can see that it is the identifier for the working memory element, and which is why we said that maybe you will find it useful to give them names and then say that change in those names.